Hi, my name is Rob Lyerly, and I'll be presenting the work in OpenMP Runtime for transparent work sharing across cache-incoherent heterogeneous nodes. This work was done with my co-authors Changwoo, Christopher J. Rossbach, and Binoy Ravindran. This graph shows 48 years of microprocessor trend data. We can see from this graph that although CPU manufacturers have continued to increase the number of transistors they put into their designs, metrics such as single-thread performance, frequency, and power consumption have slowed. This has led CPU manufacturers to strike different designs in trying to balance single-thread performance, power consumption, and parallelism. As an example, Intel's Xeon processors tend to have fewer, beefier cores, whereas Cavium's ThunderX line of ARM processors tend to have smaller cores but larger numbers integrated onto a single die. Even more recently, we've seen integration of multiple different types of processors into a single package. For example, Intel's Agilex platform integrates Xeon CPUs with an Agilex FPGA, which itself includes ARM processors. The question that naturally arises when integrating all these heterogeneous computing elements together is how do we best program these systems? So a natural first choice would be MPI, which has been called the assembly language of high-performance computing. MPI is especially painful in heterogeneous systems. First, MPI requires users to manually tune the work distribution across these heterogeneous cores, which becomes even more painful as different applications can perform differently on these different processing elements. Additionally, users must manually manage their memory that goes along with this workload across separate physical memory regions. More recent work, such as K2 and Popcorn Linux, instead propose using distributed shared memory to automatically migrate data to where it's needed for applications. So on the right-hand side, on the upper part, you can see an example of Popcorn Linux's single writer, multiple reader page coherency protocol. Popcorn Linux's compiler is responsible for transforming an application state to be migratable between different ISAs. Meanwhile, Popcorn's distributed shared memory is responsible for bringing data on demand between nodes by intercepting page faults inside the kernel. So, given a system that automatically allows us to migrate between heterogeneous ISA CPUs, how can parallel workloads automatically and transparently leverage these heterogeneous processing elements to maximize performance? As an example, on the bottom of the right-hand side, we see three separate benchmarks run in three different workload configurations, entirely on x86, entirely on ARM, and using a combination of the two together. So we can see that no single workload configuration is the best across all of these benchmarks. So how do we automatically and transparently leverage these heterogeneous processing elements? The answer is our new runtime libhetmp, which uses OpenMP to automatically work-share parallel computation across heterogeneous ISA CPUs. Let's talk about the design and implementation of libhetmp. libhetmp is designed to allow users to very easily leverage the computing resources of heterogeneous ISA CPUs. Additionally, the main goal is to automatically balance workloads across these heterogeneous processing elements in order to maximize the performance for parallel applications. And it uses Popcorn Linux under the hood to support that cross-ISA execution. libhetmp organizes threads into a hierarchy. It considers threads as part of a node in which all of the cores of that node are cache coherent, roughly equivalent to all of the cores that have the same instruction set architecture. libhetmp uses this node structure to create a thread hierarchy and uses that to reduce the amount of global communication across nodes. In particular, it's used for synchronization and work distribution. libhetmp adds a lot of new functionality to OpenMP's loop iteration schedulers. In particular, it adds new functionality to two existing schedulers, the static and dynamic schedulers, and also adds a third scheduler, the headprobe scheduler, specific to heterogeneous ISA CPUs. OpenMP's static scheduler evenly distributes loop iterations across all cores in the system. libhetmp extends the static scheduler to allow users to manually skew work distribution. As an example, an x86 CPU might need 3 times more work than an ARM CPU because it has better single-threaded performance. In OpenMP's dynamic loop iteration scheduler, threads grab new batches of work from a global work pool after finishing previous batches of work. In libhetmp, this is extended to use the hierarchy. Threads first try and grab work from a node local work pool. If that node local pool is empty, That thread then grabs a larger batch of work from the global work pool for all threads on that node. In this way, it reduces the amount of global communication required when distributing work. Finally, libhetmp adds the headprobe scheduler. The headprobe scheduler uses a small number of iterations to measure execution time on multiple nodes, and then, after measuring, distributes the remaining work according to the relative performance on those nodes. One of the first things that libhetmp and the headprobe scheduler needs to determine is whether it would be beneficial to run computation across both nodes simultaneously. If the computation is network bound, in other words, we're spending all of our time in the DSM layer shuttling pages back and forth between nodes, we can't actually leverage the benefits of multiple processing units together. If instead we're more compute bound, where we're doing a lot of computation per page transferred, we can leverage the processing resources and should run our parallel computation across both nodes simultaneously. In order to determine this break-even point, we ran a micro benchmark where we varied the number of compute operations executed per page transferred across the nodes. On the right-hand side, you can see the results of this micro benchmark. We determined that the headprobe scheduler became network bound when less than 256 operations were performed per page of data transferred, and became compute bound when it was 512 bytes or more. Correlating that to the graph below, where we've plotted the microseconds between page faults, we can see that that correlates to a page fault period of approximately 100 microseconds. In other words, if the application is causing page faults once every 100 microseconds, we are compute bound and can benefit from using both processors simultaneously. Otherwise, if we're causing more page faults than that, we're going to be DSM bound, and it would be better to just run on a single processor. In the former case, where we're more compute bound, libhetmp and the headprobe scheduler distributes the remaining loop iterations across all CPUs in the system, skewed relative to their performance as measured during the probing period. In the latter case, where we determine that the DSM layer is going to be a bottleneck, we instead pick the best CPU on which to run, which will have the best performance. We determine this using performance counters. For more details about our methodology and how we pick these nodes, please see the paper. Now, let's talk about how we evaluated the system. In our setup, we have a Xeon 2620 V4 interconnected to a ThunderX CPU over Mellanox InfiniBand. You can see the relative characteristics of each processor in this table. The Xeon has a fewer number of cores, but a higher clock speed and a more advanced cache. The ThunderX instead has a larger number of small processors and a smaller cache subsystem. We ran benchmarks from the Parsec, Rodinia, and MPB benchmark suites. Here we have the results of our evaluation. On the x-axis, we have benchmarks from the aforementioned suites. On the y-axis, we have speed up relative to the Xeon processor. Each bar represents a different workload configuration. Xeon represents running the benchmark entirely on the Xeon. ThunderX represents running it entirely on the ThunderX processor. Ideal CSR uses both processors in tandem, and it skews the workload distribution according to the best calculated ratio, which we determine from profiling. Cross-node dynamic is also running benchmarks across both nodes simultaneously, but uses the dynamic workload distribution to spread the workload across the two machines. Finally, the headprobe bar represents using the aforementioned algorithm, where we probe for a small number of iterations, then determine whether cross-node execution is beneficial. The benchmarks circled in green show cases where it's beneficial to run across both nodes simultaneously. Here, the application is compute bound rather than network bound. Because we can use both nodes successfully, we see very large speedups over running only on the Xeon. However, in the other benchmarks, we can see that cross-node execution is not always beneficial. Oftentimes, the DSM layer is a bottleneck in the system and actually causes very poor performance relative to running only on a single node, whether that's the Xeon or the ThunderX. So we can see that it's important for the OpenMP runtime to be able to determine whether cross-node execution is beneficial or not. libhetmp, and in particular the headprobe scheduler, is able to do this automatically and transparently without any user intervention. Overall, using the hetprobe scheduler provides a 41% increase in performance over the next best workload configuration, and is very close to the Oracle, but has small performance drops due to the probing overhead. Please see the paper for more detailed results and explanations. In conclusion, libhetmp automatically distributes workloads parallelized using OpenMP across cache-incoherent heterogeneous ISA CPUs. libhetmp organizes threads into a hierarchy, which allows the runtime to optimize its execution, including work distribution, synchronization, and reductions, by reducing the amount of global data touched. This in turn reduces the number of DSM page faults caused by the runtime. libhetmp includes the hetprobe loop iteration scheduler, which measures performance for a parallel region on a small number of iterations and automatically distributes the remaining work in order to maximize performance, whether it be across multiple nodes simultaneously or only on a single node. Using this scheduler achieves a geometric mean 41% speedup over the next best workload configuration evaluated. Finally, libhetmp is open source and available as part of Popcorn Linux.